So I'm excited today to talk to you about how we can use human input in order to develop robust AI systems. And so if we look at our world today, we're increasingly coming in contact with AI systems, whether it be through social media, recommender systems, the online advertisements that we see as we browse the web. Additionally, behind the scenes, more and more, we're starting to see robots working in warehouses and factories, fulfilling orders, helping us deal with supply chain issues. And a lot of companies are starting to think about how can we bring robots and other AI systems into hospitals, into our homes, into grocery stores, as well as into our roads and driving on our streets. And I think in the coming days and in the future, these AI systems are going to become even more prevalent. And so one of the things that really motivates my research is this idea that we want to get these robots and AI systems out there in the real world, interacting with people, learning from them, adapting to their preferences and needs. And so one of the big problems that these systems face is what we're going to call value alignment, which is basically how do we get these AI systems to do what we as humans actually want them to do. And you might say, well, maybe that's not that big of a problem. I'm pretty good at writing down objective functions, having AI systems optimize them. And a lot of objectives that we think about in robotics or machine learning do on the surface seem pretty well defined. So we can think about classification. We can say, okay, we just want to maximize our accuracy. We'll just collect a lot of data, label it, have a test set. Maybe that's a pretty simple objective. Similarly, we might think about like a motion planning problem where it seems pretty simple. We can define a start and a goal, maybe some obstacles we want to avoid. And then the objective also seems pretty clear. We want to go from A to B without colliding with something. And we also might think about robot grasping as a pretty simple problem to specify an objective for. So this is showing some of our work recently where we've been looking at how do we grasp unknown objects that may be adversarial. And here, we do give the robot just a very simple objective of a reward of +1 every time it is able to successfully grasp the object, a reward of 0 otherwise. And we use bandit algorithms to allow the system to iteratively over time improve its performance. But I think if we dig a little bit deeper into these problems, we'll see that things maybe aren't quite as well defined as we may initially think. So if we think about classification, I'd argue that no one really cares about just maximizing average accuracy. There's often subtle nuances in terms of how much we care about true positives or false positives and false negatives. For example, a driving system, we want it to be like pretty good at detecting like stoplights and stop signs, but we may allow for some error in terms of misclassifying a car as a truck. And ideally, we don't want to just have systems that can, recognize things in image, but we want to have systems that can drive down busy streets in ways that are safe and efficient. And think about what kind of objective function we'd have to write down to get an AI system to do this is actually very challenging because of all the different trade-offs and factors involved. Similarly, if we think about something like a motion planning problem, things start to get a lot more difficult if we're maybe carrying a hot liquid. Now we have all these very complex constraints that we have to take into account. And what if rather than just moving the end effector, we're now moving a person from point A to point B? Now these constraints are really depend on the person, often very hard to write down. And so this problem actually becomes very hard to specify. And then thinking about grasping, what does it actually mean to grasp an object successfully? This grasp looks okay. Turns out it's not. And really what makes a grasp good depends on how we're going to use this grasp, about the affordances that we're going to do. And really we want to move beyond just picking up an object to doing something useful, like coming into these kids' room, helping them organize, clean up their room. And we don't want it to just maybe sweep all the toys under the rug, push them into the closet. I tried that once as a kid. My mom told me, no, it doesn't match my specification. But I think she would have trouble writing down her actual specification. I would as well, of what does it mean to organize nicely and put away the toys in this room. So I'd argue that if we think about the problems that we're really excited about as roboticists and AI and machine learning researchers, that these objectives are often really hard to specify. And I'd go further and say that I would say that robust AI is really human-centered AI. Kind of going back to these problems, we really need some interaction with the person to help us figure out what these systems should be doing. So I'm going to define robustness as acceptable behavior in the presence of uncertainty and unusual circumstances. And I'd like to highlight these keywords here, acceptable behavior. I think this really brings us back to this idea of value alignment, which is, how do we get these systems to do what we as people really want? Apologies on the link. And so how does this work, though? When we're learning from people, this is often very difficult, right? People are noisy. We make mistakes. Often human input is ambiguous. And looking at what people did in hindsight often just looks very irrational at times. But I'd argue that rather than trying to minimize human input or treat human input as a disturbance, we really want to build AI systems from the ground up to think about how can we leverage human input, and how can we deal with these uncertainties and ambiguities in order to get our AI systems to behave the way we want. So kind of in a nutshell, the one-sentence summary of the work that I do is I try and incorporate efficiently human input into both the theory and the practice of robust AI systems. And kind of at a high level, I look at these three different areas, so human factors, robotics, and machine learning, working within the union of all of them, and more often than not in the intersection of these. So I've been lucky to work on a variety of really fun and fascinating problems, ranging from human-swarm interactions. How do we get humans to manage these multi-agent collectives? Looking at shared autonomy, assistive robotics, autonomous driving. How do we get these cars to navigate roads alongside humans using models of human intent? As well as looking at robust policy optimization. So how can we develop algorithms that are robust to uncertainty and really hedge against this uncertainty that they might have? A lot of my work is focused on what we've talked about, this idea of value alignment, or learning reward functions, models of human intent, as well as looking at ideas for interactive imitation learning and robust grasping and kitting of objects. So I don't have time to talk about all these today, but I'd like to focus on kind of these three topics under this kind of larger umbrella of value alignment. How do we learn specifications for AI systems from human input? And there's these kind of fundamental challenges that I'm going to talk about today. And one is, how do we estimate uncertainty? So if I'm learning from a person, how do I estimate and really think about my uncertainty and the different hypotheses that might explain the human behavior? Also talk about how can we be robust to that uncertainty? How do we hedge against risk and hedge our bets? And then finally, how do we actively reduce the uncertainty? How can we ask targeted queries that allow these AI systems to reduce uncertainty and really figure out what they need to know? And so a lot of my work builds on this idea of reinforcement learning, which I think most of you are probably familiar with, where we have an agent interacting with environment, taking actions, receiving rewards and observations. And as a lot of you probably know, this idea of reward engineering is actually quite difficult, trying to figure out what reward function we should place there to get the desired behavior is often challenging. That often is this interactive process where an engineer is going to write down a reward function, optimize it, say, oh, no, let me tweak a few weights here and there. And this is often a painful process. And there's a lot of tasks that we could say that probably showing is maybe easier than telling. So driving is a classic example where it's really hard for me to sit down and write down a reward function that describes all the important things for driving. But it's very easy for me to hop into a car and show you an example of pretty good driving behavior. And so a lot of my work looks at this idea of inverse reinforcement learning, where we're now taking the role of the observer. We're watching a human interact with the environment. We assume that they have some underlying cost function or reward function they're trying to optimize. And then the question here is, why did the human do what they did? What was the human's reward function? Ideally, we want to learn this function. We can take observations, actions, and map it to this scalar real-valued reward signal, telling us how good we think the human thinks these actions or observations are. And so you might ask, well, why not just directly imitate? If we're interested in getting behavior that's aligned with what the human does, maybe we can just watch the human, see what actions they take based on different observations, and just ask, what would the human have done in this situation? And here we might want to learn like a policy, right, that maps from observations into actions just directly using standard supervised learning. And this is well studied and often works really well. It's called behavioral cloning. But there are cases where we probably just don't want robots going through the motions. So this is a funny video I found of kind of this satirical instance of a robot just going through the motions, just kind of I know what I should do here and there, giving someone breakfast, pouring the milk. Now I'm going to pick up the spoon and feed the person. And so this is designed to be funny, but I think it drives home the point that we don't want AI systems or robots that just go through the motions and don't understand why they're doing anything. And this is not just satire. So we've actually seen this in the lab. So this is a project that I've been working on with an undergrad where we're learning how to do these assistive feeding and assistive care tasks with a human. And we tried using behavioral cloning, where we gave a couple really good demonstrations to the robot, and then we did behavioral cloning to learn a policy. However, when things changed a little bit, when the human's head is in a slightly different position, the robot starts in a slightly different position, the robot just doesn't really know what to do. It's just kind of learned to mimic the motions. It knows it should get close to the human, but because things are a little bit different than what it was trained on, it just diverges and ends up just kind of hovering over the person's head, just totally missing the mark. However, if we learn a reward function that actually maps what the human really wants and allows us to optimize to achieve that objective, then we can get really good performance and actually accomplish a task, even in different situations. So hopefully I've convinced you now that inferring human intent is important for robustness. But at the end of the talk, I'm actually going to return to this idea of behavioral cloning and talk about how we can use human interactions to make that more robust as well. So we've talked a lot about this idea of learning reward functions from human demonstrations that we can then turn into a policy via policy optimization. And this idea, like we talked about, is called inverse reinforcement learning, but there are some common problems with a lot of these approaches. One is that typically prior work couldn't do much better than the demonstrator. And this is often by design. A lot of these systems are trying to find a reward function that, if I optimize it, leads to the behavior that I saw in the demonstrator. And so we're trying to find a reward function that rationalizes what the demonstrator did, warts and all. So if the demonstrator makes some mistakes, we're going to say, hey, that was probably intentional. And we can't really do much better. Another problem is that these problems are often hard to scale to complex problems because often they have on the inner loop some kind of an MDP solver, so something that's running optimal control or reinforcement learning over and over again. So we had this idea back in 2019 that we could use pre-ranked demonstrations in order to try and address these problems. One thing that's nice is if we have a set of ranked demonstrations, so example A, which is better than example B, which is better than example C, we can now think of a reward function that tries to explain that ranking, but potentially allows us to extrapolate and think about things that might be even better than the best example we've seen. And what's cool is this is actually going to turn reward learning now into a supervised learning problem, making things a lot more efficient and scalable. So we call this approach trajectory ranked reward extrapolation, or TREX, where the idea is that we're going to take a set of pre-ranked demonstrations. Here's a simulated half-cheat environment where the robot's trying to run to the right, and we want it to run to the right as far and as fast as it can. We give it a set of examples ranging from just pretty awful, just scooting on its face, to something that's kind of like a little toddler that can kind of run long but occasionally face plants. And we give it about 15 of these examples ranked, and we learn a reward function. And the cool thing is when we optimize this reward function, learn from suboptimal behavior, we get really good behavior that runs about twice as fast and as far as the best demonstration that we've seen. So how does this work? So I'd like to kind of ground things a little bit. So what does it actually mean to learn a reward function? So this is a function, right, that maps from states S into the real valued numbers. And it's typically parameterized by some model represented by theta. It could be like a linear model or a deep neural network model. And so some examples of states, it could be like robot joints, angles, and velocities. In this case, maybe we'd want to map something like this state to a positive reward, maybe something that is face planting to a negative reward. It could also be short sequences of images if we're doing a visual task. So maybe it's a short snippet of this agent driving. And you can see here it's passing a few cars, so maybe that's like a good thing. Here it's getting passed, maybe that's a bad thing. Ideally, as a designer, I don't have to go in and specify all these numbers, but I can learn how to map from states to rewards from data. And so the way TREX works is we have a set of ranked demonstrations, and we're going to focus on just two of these. And if I prefer trajectory 2, tau 2 over trajectory 1, well, it ought to be the case that my reward function I'm learning, r sub theta, gives a higher reward to the better ranked trajectory and a lower reward to the lower ranked trajectory, especially when I accumulate this reward over these trajectories. And so what's cool is we can now just train this using a standard Bradley-Terry pairwise ranking loss. I like to think about this in terms of kind of a binary classification problem, where you could think about the logits as the accumulated rewards on these two trajectories, and we can equivalently minimize a cross-entropy loss. And so this allows us to backpropagate into a deep neural network and train it to match up with these rankings and learn a reward function that satisfies these labels. And so what's cool about this is that given pre-ranked demonstrations, reward learning is now just a standard supervised learning problem. We've removed the MTP solver from the inner loop, making this very scalable and tractable. And so this allows us to extend this work to learn from offline demonstrations for the first time to do complex tasks like Atari games, where we don't have access to the score, but we're given a set of 12 ranked demonstrations, where this is the best demonstration in our set. And you can see that the demonstrator here is doing an OK job, but occasionally they're going to ram into cars. And then we learn a TREX policy from this, which does much better. So if we look at the game scores, which the agent doesn't have access to, we can see it's achieving a score of 520, much better than the best demonstration. So you might ask, what if you don't have explicit preference labels? And so we've also looked at ideas of learning from a learner. So if I can watch a learner over time, who's maybe like on average improving, we can actually use the timestamps of different trajectories that we've seen And this actually works pretty well to give us labels. We've also looked at work on automatically generating preference labels by adding noise into a behavior clone policy. And so I'd like to kind of take a step back, though, because I think one of the cool things about this is that we now have these AI systems that can efficiently infer human intent from suboptimal demonstrations, which is something that we see that people can do from a very young age. So there have been lots of studies showing that the humans, even from age 1 or 1.5, can kind of tell what a human wanted to do, even when the human makes a mistake. And so you can see there's obviously a lot of cues going on here. There's facial cues, kind of verbal cues, but this kid says, hey, I know what you're trying to do. Let me help you out here, and is able to put this block on there. And so I think it's really cool that we're starting to see AI systems that can do similar things, that can learn from suboptimal demonstrations and kind of infer human intent, even if it's not optimally shown. So I'd like to now talk about how do we estimate uncertainty. So we talked about T-Rex, which is a cool way of learning reward functions from human input, from suboptimal ranked demonstrations, but it's only learning this single reward function estimate, this maximum likelihood estimate. And so this can lead to problems. So we found that when we trained on some human demonstrations of Mrs. Pac-Man, this is actually what the agent learned to do. So it learned that there's this cool little loophole that you can go through this tunnel, and it confuses the ghosts really badly, and so they never eat you. You can live forever, but it never actually learned to eat the pellets. It just learned that hey, dying is really bad, living for a long time is good, let me optimize that. Similarly, for this space game where you're driving the spaceship trying to shoot enemy ships, it discovered this cool hack that you can mash your keys back and forth, and you stay out of the enemy firing lanes. You live for a really long time. You never get hit. Awesome. I'm doing really well. And not really, though. And so you can see here, these are overfit to these spurious correlations in the data. While it may be true that better ranked demonstrations do last longer, maybe do avoid ghosts more, that's not really the only hypothesis that explains this data. And there's no way of having these this consideration of alternative hypotheses if we're just learning this maximum likelihood estimate. So what would we like to do? Well, ideally, we'd like to be Bayesian. We'd like to learn an entire distribution over likely reward functions given this human data. So we can think about uncertainty and risk and entertain multiple reasons that might explain this data. And so this is a well-studied field called Bayesian reward inference or Bayesian inverse reinforcement learning, where we're trying to essentially learn this posterior distribution, the probability density function over reward functions given human data. And we can use our favorite Bayes rule to look at this in terms of a likelihood function. What's the probability of this data given a reward function hypothesis along with the prior? So here R is a reward function, D is the human data. And ideally, we'd like to be able to sample from this posterior distribution and get lots of hypotheses that match the human data. And typically, when you do this, the kind of crux of the problem is figuring out this likelihood function. What's the likelihood of the human producing data D given the hypothesis that maybe they're optimizing reward function R? And so to ground this a little more, let's say I'm in a certain state. The demonstrator takes action A, but there were these alternative actions they could have taken. And so one common way of formulating this likelihood function is to say, well, the likelihood of this state-action pair is going to be equal to this ratio here, where on the numerator I have the action the demonstrator took, and then the Q value, representing the goodness of taking that action and then acting optimally thereafter. And I divide in the denominator by the goodness of all the other actions that the demonstrator might have taken. So I'm kind of performing this counterfactual and saying, how good is this action you showed me versus the other alternatives under this reward function hypothesis? But if we think about trying to find these Q values for different reward functions, this ends up being intractable pretty quickly. Because basically, it requires solving an optimal control or reinforcement learning for every hypothesis I want to evaluate. So we wanted to try and make this more efficient. And so our idea was that we could do fast Bayesian inference by taking advantage of these two components. So first, we're going to learn this low-dimensional latent space that we're going to pre-train. So we're going to learn this nice embedding space to make things more efficient. So we can go from high-dimensional inputs down to a lower-dimensional space that will make our Bayesian inference more tractable. And second, we're going to use a preference-based likelihood in order to make this calculation a lot faster and avoid having to run a reinforcement learning algorithm every time we want to evaluate a new reward function. So we call this approach Bayesian reward extrapolation, or Bayesian REX, where the idea is that we're going to do this kind of feature pre-training to learn an embedding space. So we have the same input as before with T-Rex. We have these ranked demonstrations, and they're going to be in some high-dimensional space, maybe image spaces here. And basically what we're going to do is we're going to feed these into a deep neural network, convolutional neural network, that's going to embed them down to a lower dimensional space. And so we have this feature embedding that we're trying to train. And the question is, how do we train this embedding? And so we've looked at several different ways of doing this. One way you can do this is have several different self-supervised or unsupervised task losses. So for example, we looked at trying like a variational autoencoder that tries to map from an image, embed it down, and then reconstruct. We also looked at ideas like temporal distance. So given the embeddings of two different states from the same trajectory, can I predict how far apart they are? As well as doing inverse dynamics and forward dynamics, all using the same shared feature embedding. But we found that actually just doing unsupervised or self-supervised training wasn't as good as when we added in a little bit of actual supervised learning. And interestingly, just doing supervised learning actually didn't do as well as adding in some unsupervised, self-supervised learning. I think, yeah, the intuition here that we have, and this is still kind of an open question of why, but I think the reason is that these self-supervised tasks are going to learn lots of interesting features, but they may not be actually relevant to what the human wants at all. Whereas if we just use the supervised training data, we might overfit to spurious correlations and just focus on one thing that explains the rankings. And so by having this kind of mixture of auxiliary functions, we're able to train this latent space that captures a lot of interesting information relative to a variety of different possible human intentions. And what's nice is we can now freeze these weights here, and we now have this feature extractor that works on these high-dimensional inputs. And so this gives us the feature pre-training, and we can now just define a linear reward function on top of that. So we have these features S from our latent space, and we can define a reward function as just a linear combination of these with this weight vector theta. And so what's cool about this is going to make things really efficient, because we can take these pre-ranked demonstrations that we have, we can embed them in the latent space just by adding up the latent space for every state and adding that all together. And this gives us this set of ranked demonstration, essentially feature counts in this latent space that we've learned. And so the reason this is important is because we have a linear reward function. If we looked at what our predicted trajectory return is for a trajectory tau, we're going to have to sum up all of the states in that trajectory. Well, this is essentially, if we put in the linear reward function, we can pull out the theta vector. And really all it is just this dot product. If we want to predict a trajectory's return, we just take our weight vector hypothesis, dot product with this expected feature count vector. And so what's cool is this is going to make our inference really fast. So we're doing Markov chain Monte Carlo inference, where at a high level, basically all we're asking is, given a hypothesis for your reward function, given these ranked demonstrations you've given me, how likely is this? And what's cool is we have these preference labels, right? This is kind of our input data. We want to say, how likely is this trajectory preference? Well, if we looked at the predicted returns, so I have a theta vector. I want to say, how likely is it that you were operating on this reward function? Well, if you were, then probably you would have had a higher reward for the better ranked trajectory. And I can quickly calculate how well this theta vector matches up with your preferences just via these dot products. And the only thing I need to vary is theta because I've pre-computed everything else. So this makes it nice. We can now use this likelihood function that's based off these preferences. And with just a couple dot products, we can efficiently evaluate the likelihood of any hypothesized reward function without having any need of touching the MDP, no rollouts, no MDP solver. And so this allows us to repeatedly sample from this posterior distribution really efficiently. And this is cool. This is the first Bayesian reward inference algorithm that's able to scale to these visual high-dimensional control tasks. And to give you an idea of the actual efficiency here, so we're able to generate about 10,000 samples of likely reward functions in less than a minute, just running on my laptop, no GPUs or anything fancy. Whereas if I were to use a standard classical Bayesian IRL approach that would sample a reward function, run a reinforcement learning algorithm, evaluate a likelihood, we're talking maybe 5 or plus hours for a single sample. And so this is cool. So this allows us to do this efficient Bayesian inference on these high-dimensional control tasks for the first time. And this works really well. So this is like learning an Atari breakout game. And so you see here the agent is able to learn from just a set of ranked suboptimal demonstrations in order to be able to play the game really well. And compared to some other approaches, so if we look at the best of the 12 demonstrations, these demonstrations actually never are that good. This is actually a quite complex game when you start hitting the higher and higher levels. And just running behavioral cloning doesn't do that well. You can look at some other approaches, such as a generative adversarial approach. And these methods are often really unstable and are hard to apply to these visual domains. If you look at T-Rex, it does much better. And Bayesian Rex, which is actually learning this posterior, if we take the the mean reward function from this posterior and optimize it, we actually often do even better than just learning this like MLE estimate. And so just using the reward function in this way, like just taking the expectation of the distribution is not kind of the best use of having a full Bayesian posterior. So we've also looked at what can you do when you have this posterior distribution. And one of the nice things you can do is you can come up with these high confidence performance bounds. Given a policy or trajectory, I can now with high confidence tell you whether this policy is better than this other policy using this distribution. We've also shown that we can use this to detect misaligned reward functions. So look at this example here from this bean rider example. If I have a distribution over likely reward functions, I can now take a policy such as this one, and I can evaluate it very efficiently because of this linear reward function over a variety of different hypotheses. And we found that looking at the tails of these distributions actually is a really good indicator of when this agent is performing this kind of reward hacking behavior, optimizing a misaligned reward function. Because essentially having really long tails tells me that there are lots of reward function hypotheses that looked likely given the data, but they might say that this is really bad. Because maybe these other reward function hypotheses say that like, destroying enemy ships is important or advancing through the levels. And so by having this distribution, we're able to identify cases where we might be very misaligned. Cool, so I'd like to now take a step back and think about, given that we can now estimate these reward function distributions, how can we be robust to this uncertainty? And so we're going to assume that we can now sample a posterior distribution of likely reward functions given this human data. And the question is, given that I'm uncertain over what the true objective is, how should I act? How should an AI system act if it doesn't know its true objective or reward function? Ideally, we want to have systems that are robust to this uncertainty. And so a lot of prior work typically would optimize for a single reward function. Maybe it would be like the most likely reward function, or maybe the expected reward function under a distribution. And we've seen examples, right, where the most likely reward function just like overfits to spurious correlations is not what we want. Similarly, I'd like to argue that we often don't want to just do well on expectation. So if we think about maybe like a self-driving car, driving down the road, maybe it detects some obstacle, maybe a box in the road. And it might be that with high likelihood, it thinks an expectation that box is empty, it can just run over it, nothing will happen. But there's some chance that maybe if it runs over that box, maybe it contains some object that might damage the car or hurt the passengers. And so rather than driving through, which might in expectation work the best because it minimizes weaving on the road, it gets you to your destination a little faster, we probably want our systems to be a little more risk averse. Maybe slow down, actually avoid that object. And I think that's probably what most of us would do when driving down this road. And so we turn to finance to think about how can we deal with this idea of thinking about risk, think about risk and reward trade-offs. Because in computational finance, that's really kind of the name of the game. And there are a couple of different metrics that are often used in finance. One is this idea of a value at risk. And so this is essentially just like a 1 minus alpha quantile outcome. And so if we're looking at this random variable x and we have some distribution, the value at risk is given a certain alpha level is going to be the level at which we have, say, like 95% of the distribution above that point. And so if you think about this in terms of like performance, we might be able to say, hey, 95% of the time, my performance is no worse than X amount. So kind of just taking this like percentile shop. Now, this is nice, but it turns out optimizing for value at risk actually ends up being a difficult problem, and it ignores the tails. It ignores what's going to happen in this red section, maybe in like the 5% worst case outcomes. And so often what people have been doing, and more this is becoming more popular, is this idea of conditional value at risk. So we're going to condition on being kind of in this tail of the distribution, this red shaded portion, and we're going to say, given that I'm in like the 5% worst case outcomes, how much do I expect? What do I expect to happen? So we're looking at this expectation. And so we might say that, how bad is my performance going to be in expectation, given that it's like the 5% worst case? And what's cool now is maximizing CVAR ends up being a very tractable optimization problem. And we're actually taking into account kind of the tails of this distribution, really thinking about how do we be robust to some of these kind of worst case outcomes. And so we propose this approach called Bayesian robust optimization for imitation learning, or BROIL, where basically what we want to do is we want to directly optimize a policy to be maximally robust to a distribution over reward functions. So rather than a standard RL approach that assumes that I have this magical reward function that's given to me that's perfect and I can just optimize that, we now say, okay, let's take a step back let's assume this reward function isn't perfect. In fact, let's just say we have a distribution over reward functions. Now we want to optimize our behavior such that we can maximize this conditional value at risk when these reward functions are taken from this distribution. And so the way we do that is we're going to try and make sure that we're not performing really poorly under any one of these reward functions, because that will lead us to have a high conditional value at risk. And what's really cool is we've shown that you can actually efficiently solve for a policy that optimizes the objective just using linear programming. So it's super efficient, as long as you have a discrete MDP, so discrete states, discrete actions. And what's even more cool is that you can actually extend this continuous states and continuous actions really easily using a PPO-style policy gradient. And so we have some recent work showing that with just a few changes to a standard policy gradient algorithm, we can actually now make it robust to an entire distribution of reward functions and use kind of all the standard tricks that we use in our state-of-the-art reinforcement learning algorithms to make this scale to interesting problems. And it's kind of a cute example of this. We've shown that this is really nice for hedging against multiple objectives. So we looked at this Atari boxing game where there's kind of these competing objectives where I'm trying to score points on the opponent but avoid getting punched myself. And we gave some suboptimal rank demonstrations, ran Bayesian recs to get a posterior distribution over likely reward functions. And then we evaluated a whole bunch of different approaches to try and get a policy. So we looked at risk-neutral approaches like behavioral cloning, methods like adversarial imitation learning. There are risk-averse versions of adversarial imitation learning. We looked at maximizing the most likely reward function, maybe the mean reward function. And across the board, everything performed much worse than the Broyle approach, which is trying to hedge against its risk, kind of playing whack-a-mole with the different hypotheses that it might have, and really trying to find a reward function that performs well across the distribution, allowing it to balance these multiple competing objectives. And so I think this is really exciting. And I think kind of the high-level take-home message here is that AI systems that hedge against their uncertainty are going to be a lot more robust than ones that try and uniquely identify one reward function that they think explains the human data. And I think this is really important because a lot of problems that we think about are inherently kind of multi-objective. And that's like a natural way to think about them, a natural way to express them. And really having these methods that can balance these different objectives is really important, especially if we think about ideas like aligning behavior to multiple people. It's kind of like multi-agent value alignment problem. I think extending these ideas that we have for Broyle to allow systems to perform well under multiple people's preferences is really exciting, making sure that we're not performing really poorly or under some small subset of these people's values. Cool. And so with that, I'd now like to pop back up and then move on to this question of how do we actively reduce uncertainty? Because it might be the case that I just have so much uncertainty that even if I try and hedge all my bets, it just kind of leads to something nonsensical. I just really need more information. And so ideally, we have these AI systems that can ask for help. And I think anyone that's taught a class where none of the students respond, none of them ask questions, I think this is especially pertinent in Zoom days when you wouldn't even see half the people in the audience. It's really hard to be able to tailor the information that you're giving if you're teaching a class or giving instruction to someone, and they never ask you questions, never show you what they're uncertain about. And ideally, we want our AI systems to move from being passive learners to being active learners that will figuratively raise their hands, maybe with a robot actually physically raise their hands and ask for help. We want systems that know what they know, but also know what they're uncertain about. And this will allow people to give the appropriate information and allow them to learn much more efficiently. And so the question here that we wanted to look at is, when should a robot ask for help? And so when we started thinking about this, one of the things that first came to mind was that if the robot finds itself in a novel state, then this is a point where it should ask for help. So for example, maybe I've given a lot of data of a self-driving car to a self-driving car driving down roads, but now it finds itself off-road. So because it's off distribution, it's probably going to make a mistake. And so it should probably ask for help at this point. It should probably call into the person and say, hey, can you help me out? I'm not sure what I should do. And so it kind of makes sense that novel states are going to be risky, and we should ask for help there. What we also realized is that there actually are other states. It may not be novel, but still are risky. For example, you could think about this narrow mountain pass that I've seen lots of examples of driving down, but I know there's a very small margin for error. And I know I'm still not that great at driving here. And so even though this isn't novel to me, if my policy's performance is not kind of up to snuff, I still might think this is risky, and I might benefit from some human interventions and some human help. And so we wanted to look at this and allow these robot systems to ask for help in states that are novel and risky, and allow that to improve their policy. And so we had this idea of using interactive imitation learning, where, if you remember from before, we're basically taking this behavioral cloning approach, where we're going to directly map from states to actions, we're going to learn from data, and transfer that into a policy. But crucially, we're going to maintain our uncertainty over what we think we should be doing and use active queries in order to try and reduce that uncertainty and improve our robustness over time. And so this is one of the example tasks that we looked at, where we're trying to pick up this washer here on the left, place it on this peg down here on the bottom, and there's some kind of inherent bottlenecks here, where it's often a little tricky to grasp that washer exactly right. And then when we bring it over here, there's like kind of a small margin for error in terms of placing it on this peg. And so we found this a nice test bed for testing out these ideas of novelty and risk. In particular, we call our approach ThriftyDAgger. So this is an interactive learning approach where we're going to be iteratively collecting data from a human and using that to improve our model. And so we assume that we have this human operator that we can kind of call into, kind of like a call center type approach, and ask them to come in and help us out. And in particular, we're going to take as input here our state, as well as some hyperparameter that determines how often the human wants to be bugged, or kind of how much effort they can invest in helping us out. And we're basically going to take these and we're going to ask, is this state novel? And so here's an example of a novel state where the robots ended up grasping this washer in kind of an awkward position. And if we detect this as novel, we're going to ask the human for help. They're going to come in, teleoperate the system, get us unstuck. If it's not novel, we're going to then check, well, is this risky? Based off previous data, and we're going to assume here that we have some binary indicator of task completion. And so we can train in states where we've seen a lot of data, this kind of risk metric that tells us how likely am I to be able to complete this task from this state. And so if risky, we're also going to ask for the human operator to come in and help. So for example, in this case, this washer is in a really awkward position. The robot doesn't think it's going to be able to complete this task. However, if it's not novel and it's not risky, we're going to let the robot just operate, do its own thing, and roll out its policy. And crucially, it's always going to take the human intervention data, use that to improve its policy over time. And the reason we have this kind of a gating approach is that if the state is novel, we haven't seen much data there, so we really can't trust our risk metric. And so we're just going to immediately kind of say, hey, human, I need help. If it isn't novel, then that's where we're going to look at this risk metric and say, OK, how likely am I to succeed? And if I'm very unlikely, I'm also going to ask for help. So to kind of ground this, so here's an actual execution of the algorithm where it starts off in autonomous mode. It's going to go down and try and grasp this washer, but it misses. And so it detects now that this is a novel state. It's going to ask for human supervision. We come in and teleoperate the robot. At some point, it now detects, OK, I'm back in distribution. Things are not novel or risky anymore. Takes over, switches back into autonomous mode, lets the human go do their own task, and finishes the completion of putting the washer over the peg. Here's another example where just right at the beginning, just due to the initial state configuration, the robot detects that this is risky for it, that it doesn't think it's going to be able to grasp the washer. And so it asks for human assistance to help it get lined up. And then at some point, it detects, OK, not risky anymore, not novel anymore, switches into autonomous mode. The human can go back and do their own thing. And then the robot is able to successfully, autonomously complete this task. And we've also looked at kind of scaling this up to more complex manipulation. So we're looking at this kind of deformable manipulation. We're doing this complex kind of figure-8 rope manipulation, kind of figure-8 tying task. And here we're using this Da Vinci surgical robot to give the demonstrations and interventions. And we find that because this is such a long horizon task, and we're using pixel input to try and train the robot, that behavioral cloning approaches really just can't make very much progress at all with an equivalent amount of data. But what's cool is if we use kind of an equivalent amount of data but have active queries, so we have this system actually asking for help in areas where it needs help, we are able to get often really good, fully autonomous executions of this long-range task. And what's also nice is even at execution time, if the robot ever detects that it's in a novel or a risky state, it can always ask for help to get unstuck. So you'll see here as it's coming around for this last bend, it's going to get slightly stuck. It switches back into supervisor mode. We apply just a simple correction. It then takes back over autonomously and is able to finish the task. So one of the motivations for this project was this idea that it's becoming increasingly more common that we have these kind of call center type situations where we have one or a small number of people managing large fleets of robots. So all these companies up here are actively working on or actually deploying systems like this, where they have a small number of human operators that are helping out robots, whether it be like autonomous forklifts or cars. And if we have a small number of human operators managing a huge fleet, we really want to care about how much burden do we put on the person. We can't have these people micromanaging every single robot. And so to kind of test out whether this ThriftyDAgger approach really helped in these situations, we designed a simple user study where we had 10 subjects come in, and we asked them to control 3 different robots in simulation. They were all performing this kind of washer peg insertion task at the same time. And we looked at 2 different approaches. One was a robot-gated approach, which is like ThriftyDAgger. And we also compared to some other prior approaches where the robot is the one asking for help. It's actively asking for help from the human. When it's not asking for help, the human can do their own task. And so we gave the human this task of doing this concentration game, this memory matching game where you flip over tiles and try and find matches. We also compared this to a human-gated approach, where the human is now micromanaging everything. They can see little thumbnail views of all the different robots. At all times, they can switch to whatever robot they want. At any time, they can come in and provide an intervention if they think the robot needs help. And so you can see here the different approaches that we looked at. And we found that, so HTDAgger is the one where the human gets to decide when they intervene. SafeDAgger, LazyDAgger, and ThriftyDAgger are all active robot-gated approaches where the robot decides when they need help. And what's cool is when we looked at the qualitative results after this, we found that overall, people found ThriftyDAgger to be much lower in terms of the mental demand and much lower in terms of frustration. So they weren't constantly being thrashed where the robot was querying for help, letting them go back to concentration, then querying for help again. And they also were able to accomplish their task, and the robots only asked for help when they really needed it. And what I think is even more cool, if we look at the quantitative results, we found that compared to the next best baseline, that ThriftyDAgger had 21% fewer human interventions. And so this allowed the human to do their task better. They got 57% more concentration pairs found. But there was this really cool synergy where we actually had the robots doing better as well. And so because the robots were actively asking for help at the right times, the human was able to do their tasks better, and the robots were able to get more throughput as well. And so I think this is really cool thinking about future applications where I think more and more, like I said, we're going to have small groups of humans managing fleets of robots. And I think it's really important that we have these robots ask for help in ways that minimize the supervisor burden, but also allow these systems to be robust and safe. Cool. So at this point, I'd like to kind of think about where do we go from now? So what kind of ideas am I excited about in the future? And kind of popping back up to our original statement at the beginning, I'm still very interested in this high-level goal of using human input in order to enable robust AI systems. And we've talked a lot about today kind of learning models of human intent, right? Learning these reward functions from human data. How do we represent our uncertainty over the reward function? How can we be robust? And how can we actively reduce that uncertainty? I think if we think about kind of this end goal of trying to get these systems out in the real world, interacting with people, there's a lot more than just kind of understanding these reward functions. If you think about these problems I talked about at the beginning, there's all sorts of different facets of uncertainty that we really want these systems to be able to deal with in order to be safe and robust. And so I think there's a lot of really interesting future directions building off this work. And so if we think about uncertainty, I've talked a lot about how we can model efficiently reward function uncertainty or even action uncertainty. But there's also uncertainty that these robots are going to have over their dynamics, over how the world works, over object properties and affordances, and even uncertainty over human rationality. How rational is a human? How good are they at giving me this type of feedback? And ideally, we can use efficient interactions with people in order to help robots reduce their uncertainty and manage their uncertainty in all these different aspects. If we think about human input, I've talked a lot about demonstrations and preference rankings, but there's so much more that we can leverage in terms of how we learn from people on a day-to-day basis. So I think about how I might learn from you or how you might learn from others. We often learn from natural language. Maybe we might learn from an e-stop, where I just tell you, hey, stop, you're about to do something bad. We can learn from corrections, even just looking at body language, gaze and facial expression. So I'm really interested in figuring out how we can leverage and fuse these disparate modalities in order to learn better and reduce our uncertainty. And I've also talked a lot about robustness. And in particular, kind of the focus of the talk today was on these ideas of robustness in terms of performance bounds or being robust to a distribution. But I think robustness also is very tightly coupled to these ideas of verification and certifiability and also explainability and interpretability. If we really want to have systems aligned with what we want, we need to be able to introspect and see and make sure that they can explain and that we can interpret their behavior. And so some of the things I'm excited about in the future are active queries that target different types of feedback. And so in particular, if we're learning from multiple different ways a person can give us information, it'd be great if these AI systems could actively ask, not just for good demonstrations, but even think at a meta level of should I even ask for a demonstration now, or maybe I should ask for a correction. And to do this, you have to think about how good is the human at giving me corrections versus demonstrations? How much cognitive burden is there going to be on the human? Because I want to minimize that, but also how much information gain can I get? That's going to depend on how good the human is at giving these different types of feedback. I'm also really interested in looking at how we can leverage efficient interactions with the human to enable RL systems to more safely explore. And in particular, how can we learn constraints from human interactions in efficient ways that allow these systems to be able to learn autonomously more efficiently by allowing them to kind of remove areas of the state space that are dangerous or that might be constraining. And I think a lot of the stuff I talked about today about learning reward functions can be extended to learning maybe constraint functions and things like that. And finally, I'm also very interested in this idea of interpretability and explainability. So we've done some work in the past for the T-Rex paper, trying to kind of introspect into what these neural networks have learned. So one of the ways we looked at was finding observations that the network predicted had maybe a minimum or a maximum reward. So in this case, this was an observation that had predicted low reward, where you can see that these cars are making more progress, and so it's kind of falling back. And so that was kind of a good indication that this system had kind of learned the right thing. However, for this breakout example, when we tried to see kind of what things the Atari agent was paying attention to, we found out that really all it was learning to do was just count bricks. It actually had never learned to detect that moment when the ball hits the brick. And so this is an interesting kind of correlation and a problem with this system that we were able to kind of uncover by doing some introspection. And so I think developing more tools that allow us to figure out whether these AI systems are doing the right thing for the right reasons is very interesting to me. In particular, I've done some kind of preliminary theoretical work during my PhD on this idea of machine teaching for reward learning algorithms. So how can we design a maximally informative set of demonstrations that we can give to an AI system to teach them a particular reward function? I think you can also think about flipping this on its head and think about how can an AI system design a maximally informative set of data to give to a human to show it what it's learned. I'm also very interested in this idea of trying to design these drivers tests for AI systems. So once again, we've done some really interesting preliminary stuff on kind of the theory behind this idea, what we call value alignment verification, where we're trying to design these really efficient tests that we can give to an AI system, and based off its answers, we can verify whether it's going to be aligned with a human's intent or not. And I think there's a lot of interesting work to go here where we can try and design these unit tests or drivers tests for these AI systems. And so I think there's a wide variety of applications that can benefit from these types of approaches, ranging from robotics to rehab and assistive robotics, looking at dealing with medical healthcare records, trying to learn good, robust policies, and even online education. A lot of my work has been on how can we get a human to teach a robot, but I think you can also think about how we can get an AI system to teach a human and kind of flip the tables there, and I think there's a lot of analogies that can be made. So with that, I'd like to end by thanking all my brilliant collaborators who have had the privilege of working with, and I'd like to open up for questions. Thanks. Yeah, one of the problems that I kind of showed is that if we just have these pairwise preferences, we're hoping that we can extrapolate in the right direction, but sometimes we don't. And so I think, yeah, leveraging a little bit more information, I think could definitely make these approaches, work even better.
In your experiment, do data come from humans, or are they coming from trained RL agents?
So we've looked at both. Yeah, we've looked at humans giving kind of pedagogic demonstrations of here's something really bad, here's something mediocre, here's something as good as I can do. We've also, for a lot of our big experiments, just checkpointed RL agents to kind of simulate different levels. And yeah, and we found good results using both approaches. But I'm definitely, super interested in the future in, digging more deeply. I think we haven't still done, sufficient work on the human factors side of this. in terms of seeing like how burdensome is it for a person to give ranked demonstrations. I mean, I think sorting a whole bunch of demonstrations is probably not what we want people to do. But if I'm giving maybe demonstrations in a sequence, I think it's very easy for a person to say, hey, that was worse than last time, or whoops, I really messed up, or hey, I like did really good, and give you kind of these like pairwise preferences in a sequence. We've also found it's like pretty easy for a person to kind of like be pedagogic and say like, here, let me show you like something bad. Okay, here's something better. Here's something like even better than that. And so kind of online, giving these preferences. And I'm also very interested in like just watching a person learn how to do a task over time and seeing if we can kind of use that to also get more insight into what they want. We've shown good results watching an RL agent learn over time, but haven't like extended that to actually watching real people learn, which I think is like an interesting kind of area to see if that would work. It's a great question, yeah. Yeah.
How do you solve for in fields where you want to achieve better than human performance or better than state of the art? How do you solve for like reaching another ceiling of performance when you use basically demonstration coming from human?
I'm sorry, can you?
If you use demonstration coming from human,
yeah.
Don't you run the risk to cap the performance level? And how do you solve for it in field where you want to reach like another level of performance?
Yeah, that's a great question. Yeah. So if I understand right, you're asking like, how do you achieve this kind of superhuman performance? And so I think it's difficult. One of the ways that we've found that is kind of a natural way to get around that is rather than kind of asking the human for demonstrations and trying to directly imitate that, is we can ask for these preferences over demonstrations. And then that gives us some sense of kind of what things the human maybe was trying to avoid, what things they were trying to do. If I can kind of figure out what makes one trajectory better or worse than another one, then hopefully I've kind of attached onto like the key things that make things good or bad. And then if I'm like a really efficient or really fast or really dexterous robot, maybe I could do the good things more and the bad things less. And so we found that this is like one way of achieving that kind of like better than demonstrator performance. Yeah, great question. Yes.
So in the slides on this like efficient Bayesian T-Rex, it seems that one of the benefits of T-Rex is that you need very few demonstrations to achieve good performance. But then you have this new development of training the CNN to learn the embedding. So how do you, like, how much more data do you end up needing?
That's a good question. So for the Bayesian Rex work, so we actually used the same data that we had collected for the T-Rex paper. And then we just applied these self-supervised and kind of unsupervised task losses on top of that. Because we had found that just kind of using the supervised rankings to try and learn this embedding didn't work that well. And so we wanted to have like a richer embedding space because remember kind of the key idea here is that we wanted a rich posterior distribution that would think about multiple hypotheses to explain the data. And so, yeah, so we're learning this latent space using these demonstrations, but also taking the demonstration data and we can train like an inverse dynamics model, a forward dynamics model. We can do like these kind of unsupervised kind of like autoencoder type losses on that. I think because we had like a wide range of demonstrations ranging from like really awful to like, decent, that gave us a lot of good data for training these auxiliary losses. But I definitely think as, some situations you probably could also benefit a lot. Probably in all situations you could benefit a lot from having some offline data as well, which the agent could maybe explore, maybe with some intrinsic motivation or some random interactions, or maybe just from like prior data that you have. I think you could also use that data to try and learn this embedding function, and that would help you also do the better Bayesian inference. Yes?
The robot asks for help and the human takes over for a while. Is it possible for the human to tell the robot, okay, now you should be able to figure it out from here? Or is that something that only the robot decides when it doesn't need help anymore?
That's a great question. So, so what we looked at was where the robot got to decide when to call in for help, and the robot got to decide when to like let the human go back. But I think that's like a really interesting idea of having the human like say, okay, like I'm gonna like just like let you swim now. Let's see how well you do. And we did not look at that. But I think that's like a really interesting question about like yeah, how can the robot kind of use that like signal from the human maybe to learn better about like, yeah, how much uncertainty it should have in different states or what it should do. And yeah, I think that's often what we as people do, right? Like when we're kind of like, I'm teaching my kids. So I have 3 kids, and yeah, I was teaching my daughter how to like bicycle a couple years ago, and I would kind of be pushing her, and then be like, eventually I would like let go before she said that she was ready, and she'd be pedaling along because I was like pretty confident that she could do it. And so I think we as people often will like say, okay, like now you try it now. I'm gonna stop helping you. And yeah, I don't know of much work looking at that, but I think that's really interesting. Yeah.
Another question will be, we saw different situation and like about financial market risk reward and like transporting a robot transporting some things. How do you kind of normalize risk and in the way that you input it into robot? Like how do you categorize different situations in terms of risk?
Yeah, I think that's a good question. So we're using these financial models of like value at risk, and there is kind of this like hyperparameter for a lot of these models, which is like this alpha, which kind of determines like how far out into the tail you kind of care about. And typically people just kind of set this at like 5%, like care about like kind of the 5% worst case outcomes. Let's optimize my conditional value at risk there. But I think depending on the situation, people's risk aversion definitely changes. And so I think, yeah, figuring out algorithms that can like allow you to calibrate to a person's risk aversion could be really interesting. I mean, we're kind of just like assuming in a lot of our work that the human's just like optimizing some reward function, and we're trying to learn from preferences like what that reward function might be, or from demonstrations. But you could also maybe try and learn a person's level of risk aversion, I think, from watching demonstrations or looking at preferences. And so, yeah, so that's something that we've kind of just like set as like this hyperparameter, but I think in practice you would definitely want to adapt to the domain. I think that's like a nice thing is that if you can adapt that, you now have AI systems that can range from being like purely kind of like maximizing expectation to like purely being like robust. And we have done work looking at this kind of efficient frontier between these two extremes. And so by varying these different parameters in the models, we've actually looked at if you take like a convex combination of objectives where one objective is just maximize expectation, the other objective is maximize CVAR. And you can take like a weighted combination of these to kind of carve out this Pareto frontier of policies that range from things that look good in expectation but maybe have like wide tails to things that like look worse in expectation but like really hedge against risk. And I think, yeah, thinking about like ways to like show that to a person and help them figure out where on that efficient frontier they want to be is like an interesting area of future work. Yeah.
To fail when there's risk. So like if you don't have a scalar risk function, or like the value that you're plotting in the CVAR plot isn't a scalar, then what do you do? Does that question make sense? Like if
saying,
there
so
are
what
many
if
things you care about that could go wrong, and you can't combine the way that those different things pose a risk.
Yeah, so kind of this like multi-objective, where you have like two different like risk metrics, you say, or like two different like evaluations of risk. Yeah, that's a good question. So we've been looking at cases where we do have this like scalar notion of risk. And yeah, I'm sure someone's probably looked at that, but off the top of my head, I don't know how you might deal with that. But I think that's, yeah, an interesting question. Yeah.
So this is not my area of expertise, so it may not be a great question, but a lot of these you're doing with a lot of human interactions. You have the robots feeding people. What happens when you find your system and you have your set of reward functions, but there's like a very possible negative outcome, like where you won't satisfy, maybe your reward function is satisfied, but the outcome is possibly hurting some third member. How do you go about, like, with the set of reward functions you provided, like, I guess, is there any way to make sure you don't, like, technically you'd still be completing your reward to some highest level, since, maybe it's building something, you still built it, but in the process, like, you cause damage somewhere else. How do you balance that with your reward function, or is there a way to include that?
Yeah, so I think one way would be to take this, like, robust optimization approach that we've been looking at where it sounds like you kind of have these two reward functions, right? Under reward function A, I'm doing really good. Under reward function B, I'm doing like terrible. And so that's kind of the idea behind this Broyle algorithm is I want to optimize a policy that hedges against these two different reward functions and tries to perform well under both, and at least not terribly under either. And so I think that's like one potential approach that could be applicable in this kind of setting where you have multiple different competing objectives or competing reward functions, and you want to make sure that you're not performing terribly under any one of them. But still, you could add in, like I talked about before, a little bit of incentive just to perform well in expectation. And so I think there's lots of different kind of, flavors of this type of optimization, but in particular, I think something I'm very excited about is like, how do you balance these competing objectives? I think the Broyle algorithm is one way of doing that.
Given time limit, I guess that's it for the questions. Thanks again for